So the big question, what is mass spectrometry? Basically, what we're doing is we're weighing molecules, right? But not necessarily molecules. We're taking molecules and converting them into ions, charged particles, and calculating their mass. Okay? And the reason we use mass spectrometry is because of the three things I have outlined up here. The specificity, the molecular mass gives you information about what atoms are present. And then if we can fragment those, we get information about structure. So my mom and dad don't understand what I do, right? So the basic way of telling them is I put together puzzles. Only my puzzles are molecules, okay? So that's what we do here. Again, we go to sensitivity. We get infinitesimally small amounts of material, and we can get signal out of it. We can go anywhere from nanomoles down to zeptomoles, okay? Just infinitesimally small quantities of material, highly sensitive. And other thing is it's comprehensive. We get qualitative information, so how things are put together, what the pieces of the molecule are, and we get quantitative information, right? How much is there? As scientists, those are the two basic questions we ask. What is it? How much is there? And this is ubiquitous. You can use it across many different fields. Not only the basic scientists, biology, chemistry, physics, but other engineering fields as well, the material science people, petroleum industry, as well as the pharmaceutical industry. All of these people use mass spectrometry to answer those basic questions. And so a basic mass spectrometer can be divided up into simple pieces. The basic thing you'll understand about a mass spectrometer is it runs under high vacuum, okay? So all mass spectrometers have high vacuum. That's so your ions don't bump into neutral molecules and get neutralized, right? And then what we have here is some way to get our sample into the ion source. And remember again, we're talking about converting molecules into ions, so we have to get them charged. And then once we get them charged, we use some type of mass analyzer to separate the different M to Z ratios, which then strike a detector and we get a signal and we get a mass spectrum. Okay, so again, back to the idea of puzzles and molecules. What a mass spectrum is a plot of all the ions that reach the detector, right? And it may show the mass of the intact ion and the pieces from it. So here we see the full puzzle represented by the molecular ion and then the different pieces. And along the x-axis we have the MZ ratio, and then the y-axis is the intensity or the relative abundance of the different ions that we see. Okay? And so in the mass spectrum we have certain definitions, right? I just described the molecular ion, which is the largest mass of the intact molecule, and it contains the most abundant isotope of each element present, right? And then the base peak is the highest. So sometimes you may have the base peak and the molecular ion being the same thing, or the highest mass is the highest abundance, but that may not be the case. It may be the case that the molecular ion is lower abundance and some fragment be the base peak. Okay, and here's just the most simple example. 18, it can only be a few things, H2O, right? So we have the molecular ion and then the fragments from it, right? So now what I've described is just something that's in positive mode, but ions can be both positive or negative, right? And so with positive ions, we can have a molecular ion that's an odd electron radical cation, or we can have a protonated species where we have an even electron ion, okay, just basic chemistry. Same thing occurs with the negative ions where we have odd electron anions, or we can deprotonate things and have an even electron ion. Okay, so it's just basic chemistry. We're adding electrons, subtracting electrons, adding protons, subtracting protons. Okay, now when we're talking about measuring mass, really when we're measuring mass, we talked about infinitesimal quantities. Typically we're talking 10 to the minus 22nd to 10 to the minus 27th kilograms of material used in a machine. That's a cumbersome way to deal with these things. So what we do is we create our own system of measurement, kind of like the inch or the meter or the centimeter. It's different ways to measure. And one of the most basic ways is based on the mass of carbon. Okay? And here what we do is we define carbon to be 12 with an infinite number of zeros. Okay? And everything else is based on that. And there are different elements that have either a positive mass defect or negative mass defect. And then in the mass spectrum, we can measure nominal mass. That means 500, 501, 1000, 1001, just integer levels of mass. But we can take that to another level and call exact mass, where we have an accurate mass acquired at high resolution that's measured to 4 decimal places that takes into account the positive mass defect or the negative mass defect, and we can tell what elements are in the actual molecule. All right? And that's shown here. So you see hydrogen with the positive mass defect, oxygen, fluorine with negative mass defects, and then the various isotopes. So when we look at something at an integer mass of 28, we wouldn't be able to distinguish these compounds. But we will measure them at high resolution, accurate mass measurement. We can differentiate these three from each other. So that's why we do high-res accurate mass. It's for elemental composition. Now, what I started talking about was what we call ROOMS, regular, old, ordinary mass spectrometry. That's EI, mass spec, small molecules less than 500 molecular weight, nonpolar, volatile, right? But there's a whole world of different molecules out there that are more polar, that are not volatile, things like DNA, proteins, enzymes, things of that nature that have biological significance, right? So we got to figure out some way to get these guys into the gas phase and then get them ionized. Put a proton on them, take a proton off of them. And so what we have are what the so-called soft ionization techniques. Chemical ionization, fast atom bombardment, electrospray ionization, and matrix-assisted laser desorption ionization, or MALDI. Okay? And so these are the different ionization techniques that we use to get the molecules into gas phase and get them ionized.
So MALDI, it's very simple, although somebody got the Nobel Prize for it. I don't know if you know the story about the Nobel Prize in MALDI, but it was given to a scientist at Shimadzu of the name Koichi Tanaka. And he wasn't a very high-ranking scientist, but he came up with the most basic form of MALDI. And the Nobel Committee calls Shimadzu, and nobody knew who he was because he wasn't really a very important person. So he was promoted overnight to, chief scientific research officer with, obviously a very big bump in salary. But, sometimes when it's just a poster at a conference can end up being a method that everybody wants to use. So it's very, very simple. Basically what you do is you take your sample. It's usually, your sample is in its homogeneous phase, it's dissolved. You mix it with a solution of a matrix compound. The matrix compound, it's an organic molecule that absorbs UV radiation, and it's usually an acid. I'll show you some examples. You mix the two, and then you deposit the mixture on a stainless steel plate that has little wells in it, and you let it dry. And then you put that stainless steel target plate inside of a specific mass spectrometer. Most times, it's a time-of-flight or TOF mass spectrometer. Then you shoot a laser at that spot. The laser is aimed and focused on that spot. That produces a plume of neutrals and ions in the gas phase. There are reactions in the gas phase that result in the protonation of your analyte. The idea is that with MALDI you make ions in that little plume of, that is ablated in the vapor phase, and those ions are accelerated into a mass spectrometer. And the process is usually a gas phase proton transfer, although there's some transfer that happens inside of the clusters. But once you have ions, the ions are allowed to fly, and heavier ions are going to fly slower. Smaller ions are going to fly faster, and basically it's a race between the different ions, and you have a detector, and you measure the time of arrival. And then you calibrate the instrument to give you mass as a function of arrival time. So we're always talking about calibrating the instrument, make sure it's calibrated well. Okay, and that's why most experiments use MALDI in combination with time of flight, although it can be done other ways, okay? These are just some examples of moldy matrices, but there are hundreds of moldy matrices, okay? Synapinic acid, CHCA, DHB, picolinic acid. There are lots of matrices, and there are some matrices that work specifically well for some compounds. The reason why matrices work well for some compounds and not for other compounds is because the first step in the molding process is to form this solid solution where your analyte is embedded in the matrix. So the matrix has to be able to dissolve in the solid phase your analyte, make sure it's well dispersed in that matrix, and then if it's not, if it's just making big clumps, it's not going to work. Okay, so that process is very much trial and error, and you have to play with the type of matrix, you have to play with the concentration of the matrix, and to obtain a nice spectrum. And when I mean a nice spectrum, this is not a nice one. I'm going to show you a nice one better, but moldy usually gives you, the advantage of moldy is that it gives you singly charged species. So the spectrum is very easy to understand. If you see a peak, like here, at 12361.1, you can start by assuming that this has only one charge. It's usually one proton attached to the molecule, and then therefore you know the molecular weight right there, okay? But, so this is, for example, a mixture protein, very simple, just a calibration mixture. And you can get, singly charged species for the different proteins. In some cases, you see doubly charged, okay? So don't be surprised if you see a doubly charged. So this is the doubly charged species of myoglobin. Myoglobin has a mass to charge ratio of 16 kilodalton. If you put 2 charges on it, the mass to charge ratio is 8 kilodalton. Okay, so remember that this is not mass, but it's M over C, mass to charge. Okay, it's very easy to forget that it's and this is just a very simple mixture, but you can do moldy or more complex mixtures, and Matt and Ronhu are going to give you examples of more complex mixtures. It's not all biological examples, okay? This moldy works really well for synthetic polymers, okay? One of the main uses of moldy is polymers. This is an example of a PEG 6000 spectrum. So when you buy PEG 6000, you're not buying PEG 6000, okay? You're buying a mixture that on average has a molecular weight of 6,000. But as you can see, the mass spectrometer resolves all the oligomers, okay? And if you use an even higher resolution instrument, you're going to be able to see, in some cases, the isotopes of the oligomers, okay? Maybe depending on the type of mass spectrometer or mass analyzer that you're using. Another characteristic of moldy is that it's more tolerant to salts than electrospray. So if you're using buffers or you're using complex salts in your reaction mixture, moldy tends to be more tolerant. It doesn't mean that it's infinitely tolerant. Okay, so another question that you're going to be asked by the facility staff is, do you have buffers? What are the buffers? Is the buffer mass spec compatible or not? Okay, have you thought about that? Because some buffers are not mass spec compatible. Okay, typical example is phosphate buffers. Okay, so the other technique that is also soft, and by soft we mean techniques that don't break the molecule apart, or at least they minimize that fragmentation when ions go into the gas phase, is electrospray ionization. And electrospray ionization was not invented for mass spec. Electrospray was invented for, does anybody know? Painting cars. Okay, cars who are used to be painted with electrospray, and I think sometimes they still are. So basically, it's a way of atomizing, making very, very, very small droplets of a liquid. Okay, and people in engineering first said, well, maybe we can use this to put molecules in the gas phase, and they were using electrospray for many years, and then chemists decided to use this for putting biomolecules in the gas phase. It's a very simple experiment. The simplest form of electrospray, you have a metal needle, like a syringe needle, for example, a metal needle, and you flow liquid through that needle. The needle is biased to high potential, let's say 4,000 volts, and as the liquid goes through the needle, the charge repulsion in that needle produces the liquid to deform at the interface between the needle and the air, separating it from the mass spec. And it forms what's called a Taylor cone. It's actually pretty neat. If you Google Taylor cone or you go to YouTube, you're going to see some really interesting movies of the Taylor cone, how it forms. That Taylor cone is basically a meniscus that looks, this is not accurate actually, it has a slightly different shape. At the very end of the meniscus, you form a very, very tiny spray of droplets that are highly charged. And those droplets are pushed in this way because of the field. This is positive, this is ground. And they're pushed in this way, and then there's gas flowing against the droplets that dries out the solvent. Okay, so basically you have a droplet, your neutral molecule inside, swimming, you are evaporating the solvent, so what happens? The charge ends up attaching to your molecule that is inside of the droplet. And you end up with a gas phase ion, because now it's in the gas phase, now it's charged. And all this happens in the gap between this needle and the inlet of the mass spec. So this inlet is usually a couple hundred microns, okay? So it's a very small inlet. The mass spectrometer is under vacuum. This process happens at atmospheric pressure, okay? And this is used regularly in mass spectrometry. So just an example, this is an enzyme, and this is an electrospray spectrum of that enzyme. And it's a little disappointing. So when people started using electrospray, they realized that, well, you don't get a single peak, you get several peaks. Okay, and the reason why you get several peaks is you can attach more than one proton during the charging process. Okay, so you can have the molecule plus 7 protons with 7 charges, but you can get the 8, 9, 10, 11, and you see there are many other charge states. Okay, that is not always a disadvantage, because it's also an indicator of protein conformation. The more open the protein, the more it charges. So there's been many studies on using this for protein conformation monitoring. Okay, so it's not always a disadvantage to have multiple charging, but you need to be aware that there are going to be multiple charges. And how do you tell what the charge state is? There's software that will help you to do that, but if you want to do it manually, you just zoom into these peaks and you look at the spacing between the isotopes. If the instrument is high resolution, you're going to be able to detect the spacing between the isotopic peaks. And that's the spacing between that give you the charges. So if you have 1 charge, the spacing is 1 Dalton. If you have 2, the spacing is 0.5. If you have 3, the spacing is 0.33, and so on. So high charge states like this, you may not be able to see the isotopic envelope because the peaks overlap. But low charge states, you may be able to see them. Okay? Electrospray is very powerful. The main use of electrospray is to couple liquid phase separation techniques to mass spectrometry. So when you do LC-MS, you use electrospray for coupling it. You have a continuous liquid stream coming from the sprayer, from the HPLC. We call it LC. And then all the molecules coming out are ionized, are injected into the mass spectrometer. Okay, so just an example. Not all ions are positive, although most of the time we talk about positive ions. So this is just an example of negative mode electrospray. You see some nucleic acids. And this is a high resolution spectrum. So you can see so M minus 5 protons detached from the nucleic acid, 4, 3, and 2. And then this fine structure, these are the, so you see 1488, 1499, 1510, 1521. These are, that's probably sodiated, yeah. So one thing that you get with nucleic acids in particular are pretty challenging. Nucleic acids tend to attach a lot of alkali ions. Okay, so there's specific techniques for analyzing nucleic acids by mass spec. Okay, I think Matt is probably going to mention this. If not, Ronhu, a specific type of electrospray is called nanospray or nano electrospray ionization. It's a very low flow electrospray. This is just a little movie of the Taylor cone. It's really pretty. This is the Taylor cone, and it's used specifically for proteomics applications where you have biomolecules that are difficult to ionize and they're difficult to desolvate, or when you have very small amounts of sample. Okay, so those cases need nanospray. Nanospray is much more tricky to operate. It requires low flow pumps or low flow connections. It's a little bit of an art, but it's used also on a regular basis. Okay, in summary, soft ionization techniques can produce a variety of ion types. This is just for reference. Electrospray produces multiple charges. It produces not just protonated molecules, but it also produces adducts with sodium, ammonium, potassium, and it also produces dimers. Okay, so many times you're going to spend most of your effort in analyzing the spectra, not so much collecting the data. Okay, you need to sit down and with a calculator and try to understand what you're looking at. And then please don't forget that HPLC pure solvents are not pure. Okay, if you inject HPLC pure solvents in your mass spectrometer, you're going to get thousands of signals. Okay, so many of the signals that you're seeing in your spectrum could be just background impurities. Okay, so it's always good to correct and look for blank signals before you try to identify. If your advisor says, I want you to identify every peak in the spectrum flat out say no, that can't be done, okay? Because it just doesn't make sense. Look for it specifically what you're interested in, okay? And there are lists of known impurities that I can send you if you're interested. MOLDI is simpler, singly charged ions. You can see alkali adducts. Sometimes you can see adducts with the matrix, okay? Expect that. And you can also see matrix ions. So if you go to the very low molecular weight range, there's a lot of signals from the matrix. So the facility can do both EI, CI. Do you guys do FAB? I don't think you do anymore. So FAB is being superseded by MOLDI mostly, and electrospray, okay? So these techniques are all available, and they have specific applications. And EI and CI are mostly small molecule techniques. MOLDI is used mostly for medium to large molecules. Electrospray can be used for both, depending on what you're talking about. So there's been work where you can do electrospray ionization of an intact virus capsid, okay? So you can look at very large things, but that's not a routine experiment. I don't want you to have false expectations that you're gonna do that, okay? So with that, we're gonna talk now about once you make the ions, what do you do next? How do you analyze those ions and how you generate that mass spectrum?
So basically mass analysis. So what we're talking about here is we've taken a molecule, we put a charge on it, converted it into an ion. The reason we do that is because now we can separate the ions out based on some fundamental physics, namely momentum, kinetic energy, velocity, and frequency, right? And to do this, we use either magnetic fields or electric fields, right? Because they'll disperse based on their properties, their mass, and their charge, okay? And so in our mass spec facility, we have a sector mass spectrometer, consisting of electric and magnetic fields. We have time of flight mass spectrometers run at extremely high voltages. We have quadrupole, triple quadrupole mass spectrometers. We have ion traps, and we also have an Orbitrap mass spectrometer. Okay? And so the performance of your mass analyzer is based on the M/Z range it can cover, the resolving power, be it the nominal mass measurement or the high resolution accurate mass measurement, as well as the scan speed. How fast can we go from 50 to 500? How fast can we go from 50 to 5,000? M/Z ratio, right? Because if we're talking about coupling chromatography, be it gas chromatography or being liquid chromatography, right, we only have a certain amount of time where we can measure mass because it's defined by the width of the elution volume, okay? And then finally, sensitivity, right? What's the ultimate low amount of material we can measure? Okay, so we'll start with the first instrument, and then again, this is our sector instrument. It's a 3-sector instrument. Whoop, go back. Consisting of an ESA, a magnet, and another ESA. And this is what we do about 60% of our normal sample volume on, right? So these are low molecular weight, volatile, non-polar molecules, right? So your typical standard organic synthesis type of stuff. And on the front end, we have a GC, right? So if one was to bring us a complex mixture of samples, you could separate them based, let's see, there we go, wrong way. GC's here on the front end. It also has an auto sampler on it, so we can bring multiple samples in that are complex mixtures. You can separate them based on their volatility and then measure their masses. The next instrument we have is the triple quadrupole mass spectrometer. Okay, the triple quad is a nominal mass measurement instrument with an electrospray front end, right? So we're going to be able to measure 500, 501, 300, 301, but it's only nominal mass. The other thing is with the triple quad, as Facundo mentioned earlier, we generally with electrospray get intact molecular ions, but that doesn't give us structural information. With the triple quadrupole mass spectrometer, we can select with the first quadrupole a mass of interest, then fragment it to get structural information. Okay? So that's a very powerful technique. And then in addition, we have liquid chromatography on the front end. We can separate ions or separate individual molecular species and introduce them into the quadrupole sequentially for their measurement. This is just basic quadrupole function.
Quadrupoles are not easy to understand how they work, but the basic idea behind the quadrupole is it's a mass filter. Okay, you set it for transmitting a specific mass. It's not a high-resolution instrument, meaning that it won't separate things that are very close to each other. Usually, we're talking about unit mass resolution. Okay, it can be tweaked to a little bit better resolution than this. But you have your ion source that most likely it's a hard ionization source like electron impact. You have a set of lenses and then the quadrupole, which is 4 metal rods. Okay, and then ions go through these metal rods, and when they go through the rods during the travel time of the ions, they are changing sign, okay, voltage-wise. They're changing sign all the time, very rapidly, very high frequency. So it's like the analogy I always want to make is like walking through a hanging bridge in the middle of the jungle, but the hanging bridge is swinging. Okay, so if you walk through that bridge at the right speed, you're going to make it through. But if you try to hold on, you may just fall off. Okay, the way that we filter ions is we adjust the frequency and we change the amplitude of the oscillation of that bridge. So some ions fall out and some make it through. Okay, it's more complicated than this, but that's all that matters. Quadrupoles are very useful for quick reaction monitoring. If you don't want to do a quick mass spec experiment, you want to know if a reaction is producing something that you expect, and it's a simple mixture, you don't need a high-end mass spectrometer, okay? The ions, as they go through the quadrupole, they're going to feel either a push or a pull from the rods, okay? And they're going to have trajectories. Some of them are going to crash against the rods, some of them are going to fly between the rods, and some are going to make it through. The settings in the instrument are scanned very quickly, milliseconds takes to do a scan, but it's still a scanning instrument. It's not a very fast instrument. And you're going to get a mass spectrum by scanning the conditions in the quadrupole. Single quadrupoles are everywhere. Okay, the space station has a single quadrupole. They are in process plants. It's the most common mass spectrometer. The technology has been around for 60 years now. The more advanced form of the use of a quadrupole is what Cameron was telling you. It's called the triple quadrupole or the triple quad. It's a very deceiving name because the triple quad only has 2 quads. It's just a historical name because the first triple quad had 3 quads. But most days that now the triple quad has a first quadrupole here, which you use for mass selection. You select the ion that you're interested in. Then you have a collision cell that it's a hexapole. It's 6 rods, not 4 rods. And then you have a second quadrupole here, which people call the last quad on the triple quad. That quadrupole there is the one that can perform different functions. So there are very many cool experiments you can do. One experiment would be to fix this quadrupole for an ion of interest, activate your collision cell, and fix that quadrupole for a fragment of interest. If you are thinking about going into baseball, that's the way that steroids are detected these days. Okay, steroids are detected by using triple quadruple mass spectrometry and looking at specific precursor fragment ions of specific steroids. I know you're thinking how I'm going to beat this. Okay, so what synthetic chemists do is they add one more methyl group, so now the fragment shows at a different mass. And that test will fail because this is very specific, very sensitive for a specific molecule, and this is what we use for quantitation. If you're thinking about quantitation, this is the most standard way. For small molecules. For large molecules, it's a different ballgame. Okay, triple quadruple mass spectrometry is everywhere. The CDC has a room with 50 of these. Okay, you can do triple quadruple mass spectrometry coupled using electrospray. That right there is the electrospray ion source. This box is the triple quadruple mass spectrometer. And the front end, you can have an HPLC. This is an Agilent HPLC with an autosampler, the pumps, degassing unit, solvent tray. So basically, you load up your trace. You say, I want to quantify this specific molecule. Let's say it's a drug. I want to quantify it in plasma. You have to prepare your sample before you do that. You're not going to inject plasma directly. And then you have your mass spectrometer set for detecting that particular drug, and you can quantify. Okay? It's not so easy. This takes significant method development. Okay? But it can be done. It can be done very sensitively. The advantages, like I said, of this type of quadrupole instruments are that they're very sensitive. They're very rugged. They're simple. The technology is very well known. Okay, you can do MS-MS experiments. The experiment that I described, where you fix both quads, it's called a reaction monitoring or selective reaction monitoring experiment. But you could also keep the first quad fixed and the last quad scanning. If the last quad is scanning, you can monitor all fragments, and that gives you structural information of your molecule. Okay, you can verify the identity of a molecule, a target molecule, or you can search for molecules that have that fragmentation pattern. Okay, so many labs have this in open access mode, which is something that we're hoping to implement at some point, meaning that a student or postdoc walks into the facility and run their own sample. Okay, but you can, you need to be trained before you can do that. And cost, well, define low. It's not that low. A triple quadruple mass spectrometer is more expensive than my car for sure. This is an image of another instrument in the facility. This is, we call it, in a familiar terms, this is the Voyager instrument. It's a MALDI, time of flight instrument. This was a donation, correct? Or it was a collaboration, donation through a collaboration or something like that. It's a MALDI time of flight instrument, okay? And this instrument is useful for larger molecules like nucleic acids, polymers, proteins, intact proteins, and so on. And the basic principle of time of flight, it's my favorite technique, is very simple, very easy to understand. I don't have to talk about the jungle bridge, you know. It's basically you create the ions, for example, with a laser pulse. You accelerate all the ions so they have the same kinetic energy. If we were ions, you all start from the top of the mountain. We all have the same potential energy, and then you start running downhill. When you get to the end of the slope, you start running on flat ground. We all have the same starting energy, same kinetic energy, speeds, right? The basic equation of kinetic energy is 1/2 the mass times the velocity squared. So because the kinetic energy is constant, ions of low mass will have high velocity. Okay, and ions of low mass will reach the detector sooner. So you can do this experiment very easily. You can actually hook up an oscilloscope here and measure the ions hitting the detector as a function of time. It's very cool because you can see individual ions hitting the detector. And you can record that and average that for a while. This is just a very simple representation. Modern time of flight or TOFs are not this simple. So this is the nice ideal theory. The practical implementation is much more complex. This is actually the schematic of the Voyager instrument that we just showed you a picture of. You have your MALDI ion source, the plates that extract the ions from the source into the TOF chamber. It's usually a set of tubes, okay? And then ions fly down this tube, and they can either hit the detector. This is called the linear mode detector. That's used for high mass, medium resolution experiments, or they can fly, and there's a device here called the reflectron, invented by a Russian scientist, like anything useful. And the reflectron is used for bouncing back the ions. The ions go like this, they bounce back, and they hit another detector. And what this reflectron does, it separates ions a little bit better. It gives you more flight time to separate the ions, and it gives you a higher resolution spectrum. So when you do MALDI, you can choose to do MALDI in linear mode or in reflectron mode. Okay, but doing reflectron mode is high resolution, but you have some losses. So you lose ions, so it's less sensitive. Okay, so there are trade-offs. This is a schematic of the Voyager. This is a workhorse instrument. You still see it around. There's also another type of time of flight experiment. It's called an orthogonal time of flight experiment. So if you want to do electrospray and not MALDI, you can make electrospray ions. You see the needle here. The ions go through a series of chambers to go from atmospheric pressure to vacuum. And then they go, this is the TOF chamber. And instead of going straight into the TOF chamber like before, they go orthogonally. They go into this area and they're pushed down at 90 degrees. So they bounce into the reflectron and they go into the detector. So this is a clever way of coupling electrospray to time of flight. You can have a continuous ion stream and still do time of flight, which is a pulsed mode. Okay, so you will see this instrument, this configuration is also very common. Okay, and these are the basic types of mass analyzers. Of course, you can mix and match this type of mass analyzer, and you can have hybrid instruments. For example, if you mix two time of flight mass analyzers, you get a TOF. Okay, the TOF, and these days there's something called the triple TOF, which is not really a triple TOF. Okay, but this is a moldy TOF, and the facility has one. It's called the 4700 Applied Value Systems instrument. Basically, you create ions by a laser pulse using moldy technique. You have a TOF chamber that separates the ions. You have an ion selector that it's basically like a revolving door. Okay, you keep that door closed until the ion that you want comes, and then you open that door, and then only the ions of interest will go through. You fragment the ion of interest, and then you analyze the fragments in the second TOF chamber. So this is what's called a tandem mass spectrometry experiment, or MSMS, meaning that you do one stage of mass spectrometry, you separate ions by mass to charge, you fragment a specific precursor ion, and then you separate the fragments produced from that specific fragment ion. So this is one of the ways that, one of the technologies used for identifying proteins by sequencing peptides coming from that protein. Okay, so this is a fairly large instrument because now you have two time-of-flight tubes connected to each other. You want to say anything about the TOF? If you go to a facility, ask Cameron or Dave to show it to you inside. It's a pretty cool machine. You know, all the tubes. It's a pretty complex instrument, but the advantage of time-of-flight instruments, again, you need to talk about resolution, speed, mass range. Mass range-wise, they have very large mass range. You can look at very large molecules. Okay, we're talking about tens of kilodaltons or more. The main advantage of time-of-flight is their speed. So if you are coupling mass spec to a very fast separation, like a fast liquid chromatography, these days you have something called UPLC, ultra high performance liquid chromatography, with peak widths in the order of 10 seconds, 20 seconds. You need your mass spec to be acquiring data very quickly. If not, you're going to miss your peak, right? The peak is just going to go through the ion source and you're going to miss it, and the mass spectrometer is waiting to collect data. So that won't work. Time of flights are very quick. You can acquire spectra in 50 milliseconds, 20 milliseconds, very, very quick. You can put a lot of points across that chromatographic peak. That's one of the main things. The other thing is they're pretty sensitive instruments, okay, but not as sensitive perhaps as a triple quad, but they're pretty sensitive, and they can use for quantitation under certain conditions. That's our superstar instrument that arrived. When did it come, Cameron? The Orbit Trap. 2 years now. So this is the only new type of mass spectrometer or mass analyzer that's been reported in the last, I think, 30 years, pretty much. Okay, so the Orbit Trap, they all look the same from the outside, right? There's all like a box, a black box, and very expensive box. But the Orbit Trap, it's a very powerful instrument for many reasons. One, it provides both high resolution, means that the capability of separating closely related ions, and high mass accuracy, meaning that you get 3 or 4 decimal places in your M/C value. And that can allow you to obtain a very accurate elemental formula. Okay, so that's the first step. If you have an unknown, to at least obtain an elemental formula. This is what the mass analyzer inside of all this big box looks like. So the mass analyzer is about this big. Okay, and the mass analyzer has basically 2 parts. It has this outer electrode. This is cut, okay? Has this outer electrode here called the barrel electrode, and has this very specific shape. And then it has a spindle electrode inside. And this is a euro coin, which is about like the size, a little bit bigger than a quarter. So this is not a very big mass analyzer. And ions are produced by an ion source and injected in this direction. Okay, they come at a 90-degree angle, and there's electric potential applied here and here. The ions come at a 90-degree angle, and they get wrapped around that spindle electrode, and they start oscillating. In this case, you don't measure the ions directly. What you measure is the frequency at which they move around the spindle. Okay, and you do that by measuring the image, the frequency of the image current on this barrel electrode. So in other words, this is the whole picture. I was just showing you the mass analyzer. This is at very low pressure, 10 to the negative 10 torr usually. You can do this with electrospray or moldy. This is just an electrospray source. You make ions in the electrospray source. You go through all these intermediate stages of pumping to go from atmospheric pressure to vacuum. These instruments also have another mass analyzer before the orbit trap. You can have, this is a linear ion trap, so you could do very complex experiments. For example, you could select an ion here, fragment the ion, and then shoot the fragments into the orbit trap to measure them with high mass accuracy. And you can do these very sophisticated experiments. But the ions are basically, they're compressed here and shot into they're compressed and shot into the orbit trap. And then they start going back and forth. And the frequency of that oscillation is specific of a given mass. So you can measure frequency very high accuracy. That meaning that you can measure mass with very high accuracy. Okay, so that's the frequency, and you convert that, you do an FT, and you convert that to mass. If you have multiple ions, if this ion packet is not pure, you're going to get a signal that is not a pure sine wave. You do an FT, and you get the different frequencies, the different masses for the mixture that you injected. So this is probably all you want to know about the orbit trap, but if you have a very complex mixture where you want really high accuracy measurements, that's probably the way to go. So I'm going to
just to recap what Facundo and I have been talking about to this point. The facility has a sector instrument, magnetic sector with electric sector, and basically that instrument we use for small, nonpolar, volatile organics, typically less than 700 in mass. We ionize those by EI. Okay, we're capable of nominal mass measurement, and it's also capable of high resolution, accurate mass measurement. Okay? We can also handle complex mixtures with separation by GC. The triple quadrupole mass spectrometer that we have is good for the polar small biomolecules. We also do things like DNA on that machine. We have liquid chromatography on the front. So again, if you have a biological or a drug that you're looking for, right, you could grind up, we've had plasma, urine, feces, brain, livers, hearts, whatever tissue that you're looking in, we can find the drug molecule using that machine. Also, as Facundo mentioned, we have an ion trap coupled to the Orbi trap. So we can do, again, LC separations, nominal mass measurement, MS-MS experiments, high resolution accurate mass measurements on that machine. And then we have the MALDI-TOF and the MALDI-TOF-TOF. So you can handle peptides, proteins, polymers, enzymes, things of that nature, typically of a molecular mass greater than about 700 to 800. And then remember too, with MALDI, you're typically talking about singly charged ions, right? So the mass range can be anywhere from, like I said, 700 or 800 up to tens of thousands to 100,000 kilodaltons. But with our other instruments that use electrospray, the M/Z value is based on the number of charges. So we can take something like a BSA that's 66 kilodaltons. If we throw 66 protons on it, its M/Z value is 1,000. So depending on the number of charges you can put on a molecule. So you could have something that's super basic, has lots of lysines or arginines. It's going to protonate like crazy. It's relatively easy to see. You could have the opposite effect. Something that has lots of glutamics or aspartics on it. It's going to deprotonate like crazy. We'll look at it in the negative mode, and it'll have a small M/Z value. So it's all about knowing the chemistry of your molecule. Does it like protons? Does it hate protons? Does it like electrons? Does it hate electrons? It all helps us figure out what ionization technique we want and what instrument we want to use. So it's just basic chemistry, protons and electrons.